Okay, welcome to the second mini course. This will be on combinatorial maps, matrix models, and topological recursion. And our main goal is to prove the topological recursion for a specific case, which is the model of combinatorial maps, and which is also equivalent to the one Hermitian matrix model. And this is a very important instance of topological recursion. It's like historically, like almost the first one, I would say. It was created to solve this model. So it's first a classical example, and also not so easy one. So you will see a lot of tricks that you need to do to prove topological recursion in this particular case. And the spectral curve is already a large family of spectral curves. So it's not really like the easiest case and it's worth nothing. It's, you will see that it's not so easy. And I will try to do the whole process with quite some details. So this is the main goal. Then a secondary goal is to relate combinatorial maps to the matrix model. So you can see both perspectives. And later I will also, well later, I will actually do this quite soon, but I will finish with this probably. I will also introduce another type of special maps that will be kind of the dual of the classical maps. And this will be somehow important for topological recursion. Okay, so I will start with an introduction to maps. And this should really be a gentle introduction to maps. So sorry for the experts in maps. You can probably go to sleep or do something else. If you are too bored, you can keep an eye on the notation maybe. So please stop me if you're not understanding something, because these things are very elementary, so it should be understandable by everyone. So if you're not understanding, it's probably that I'm not explaining it well enough. So first I want to clarify that when we say maps, we actually mean maps. I mean, this name comes from maps in the geographical sense, like maps with a world with countries and seas. They also receive many other names. So they are also, we can also call them embedded graphs. This is just to clarify in case you heard some of these names. So you know that we are talking actually about the same objects. Just that in different contexts they receive different names. So they are also called ribbon or fat graphs. And maybe also discrete surfaces. Yes, so these embedded graphs, intuitively they are just graphs drawn on a surface. And the fact that they are like embedded on a surface is very important, because we can have, for example, these two graphs embedded on the whiteboard. So on the sphere projected, so on the plane, but you should just imagine it as the sphere. These two guys are the same as graphs. But they are not the same as maps, because their embedding is not the same. So here we have a cyclic order around the vertex, which is different. Okay, so this gives us an instance of a graph that gives two different maps. So the embedding is very important. So let's give the proper definition. We have X, an oriented surface of genus G. Yeah, sorry, my handwriting is not very good. I'm trying my best, but tell me if you don't understand something. We call map of topology Gn a graph that we denote gamma embedded on the surface in such a way that the complement of the graph is homeomorphic to a disjoint union of open disks. And these open disks, we call them faces. Okay, so you can already see the G, because I took a surface of genus G. But what about the N? So to say that it has N boundaries, so it has topology Gn, we actually say that we mark N faces. And what do we mean by marking? By the way, marked faces will be called all the time boundaries, which I very often write as like this. I'm a bit lazy writing. And the way to mark these faces is we'll label them from 1 to n. So they are ordered. And we also mark one of the edges. I should do it bigger? Okay. I make it stronger. Bigger. Okay.
What's the symbol after the?
I just want to know what that symbol is.
This
Yes.
one?
What's that?
It's a D with a little circle on top and a 2. And it's just an open disk
I see. Okay.
on the plane.
Okay. Thank you. Thank you.
So this is just to say that the faces, so the complement of the graph in the surface, there should be this joint union of simply connected things.
And does the graph has to be compact or not?
Yes. Yes. Mhm. Yes. But if it's disconnected, you will never have this, no? So, but okay. Also, we will usually be taking the surfaces to be connected as well, but there will also be disconnected things in the lecture. So that's why I didn't want to specify. We can have both.
Can you repeat also what you said about the marking?
Yes. I actually wrote part of it, but I have to write the rest. So we label the boundaries from 1 to n, and then we also mark one of the edges in every marked face. So to mark a face, let's just make a picture. Imagine you have a face like this, a pentagon. To mark it first, you have to give it a label from 1 to n. And then you have to mark an edge with an arrow in such a way that the marked face will be on the left.
All right, so you are saying that we have in total n faces or not?
No. So the end faces are the special faces, are the boundaries, but we will also have internal faces that are not marked.
Oh, okay.
I will give examples now, so it will be clear, hopefully. Okay, so I just finished writing it, but it's just what I explained. So containing a root. So the root is this marked edge. And the picture is like this. This should be the boundary on the left. Okay, and all this is up to isomorphism. So now I should say when two maps are isomorphic, and then I will go to the example. So if something is not clear, it should clarify it. So two maps are isomorphic if there exists a homeomorphism of the underlying surfaces. that restricts, I mean that it's orientation preserving, sorry. And that restricts to an isomorphism of graphs when you restrict it to the graph. And also we want that it preserves the roots. Not only preserves the roots, but it's the identity at the roots. Okay, so this is everything. Let me draw the drawings and then we can do questions. This is still okay, yes. Yeah, maybe I will just do it here. So this time I'm drawing the sphere. And here I have my graph embedded on it. Something like this. So okay, right now this has three faces. This one, and the exterior one. I want to mark one of them, so I just mark it saying like, okay, this will be the boundary number 1. And I have to root an edge on it in such a way that the face is on the left. So for example, this one, this will be the boundary. And these other two faces, they are called internal faces. And the boundary is of length 1, 2, 3, 4, 5. And the internal faces are of length 3 and 4. Yes, very good. This is what the examples are for people to tell me, I don't understand. So, what is not clear?
I am really sorry because,
No, it's
by the
fine.
way, I thought I knew graphs. Okay. Anyway.
Oh, no.
Right. So in this example, you are taking a graph, and this graph has two. So it's like two triangles, right?
No.
So what is the drawing? I don't
This is one triangle.
see.
This one in here.
See.
The one outside is a quadrangle.
Okay. So
Maybe I can even use another color.
I think she just meant that you were on the way of her eyesight.
you were in front of the picture.
Okay.
Yeah.
This is the quadrangle
Yes.
that you're gluing on the other side, and this is a pentagon that is glued to itself
Ah. Okay.
here. Okay, so this was the non-clear part. So actually I will give another representation, just so I can freely use both of them. So the ribbon graph representation, if you want, would be something like this. And maybe then it's clearer, this gluing of polygons that Marta was pointing out. So this is a good point because it's an equivalent way of thinking of maps. You can think of them as a graph embedded on a surface or as a collection of polygons that you glue together. So yes, this is the ribbon graph representation. I hope it doesn't make it worse, but this is the triangle, this is the boundary, that is a pentagon. So you can see here the two edges glued together, the two half edges glued together forming an edge, and then the exterior face, which is a quadrangle. Okay, is it clear? And this guy is of topology 0, 1 because it's drawn on the sphere, and it has one marked face, which is the boundary. Now let's go to a higher topology. If we draw something like this, this is not okay, because the face that is outside the square is not of the topology of the disk. Okay, so this is not a map. But I can actually fix it quite easily. I can just add some edges. And this is a map. That is fine. So it's a map of topology 1, 1. Yes, the root is this marked edge. So this is topology 0, 1, meaning that you have one boundary. How do you determine the boundary? You choose one of the faces and you mark an edge on it. In such a way, you put an arrow in one of the edges in such a way that the marked face should sit on the left.
But then you have a choice of this.
Yeah, I could mark another one. I could I could mark this one, or this one, or this one, or this one. Yes. So you have 5 choices because it's of length 5.
And could I ask also, you could have multiple roots, right? Or just one?
No,
'Cause
just
you're
one.
talking about the root, but I thought that whenever... Okay, let me clarify my question because I wasn't clear. So let's say you have n marked faces. So in this case, you have one marked face, so you have one root. But if you have 3 marked faces, you have 3 roots, right?
Yes, exactly.
Okay, so you have one root per marked face.
Exactly.
But there's not the root. It's the root for each marked face.
Exactly.
Okay.
Yes.
Thank you.
Okay, very good. Thanks for the question.
So boundary of length what? And what does the length of a face means?
This number?
Yeah.
5. Do you see it? This is, maybe it's easier to see in this picture. So it's of length 5 because it's like 1, I mean, I'm counting the half edges that belong to the boundary. 1, 2, 3, 4, 5.
Okay, and
So
face.
it's a pentagon in which you have glued 2 of the edges together. So it looks like a triangle with an extra edge.
Again, face length means of the boundary. For faces.
Yes, yes.
Yeah.
Just a question about the vertex at the glued, the vertex in the graph, which is where you have these glued edges coming out.
Yes.
What is the valence of that vertex?
This is a good point. So the valency is the number of half edges entering the vertex. So it's 3. Yes. So this one.
And then there are 2 because it goes like that.
Wait. No, because you have to count like, okay, let's say that the half edges that are incident to a vertex are the ones that are ingoing. Then this one is ingoing. This one is. And this one is. And if you, maybe it's very easy to see in here. So this is why it's nice to be comfortable with both representations. So in here you see that it's 3, like it's the natural thing to think. But you also need to understand what it means here, because we will often be talking about half edges. So you can see half edges in this picture. I hope I'm not making it worse. These guys keep falling. So you can see half edges here as like half of an edge. And you can see half edges here as like these guys have a half edge and this guy is the other half edge that form this edge.
But the number, it doesn't. So, again, sorry. I have the edge on the bottom is going into the vertex.
This one?
This is going in.
Yes.
Then I go out and in again.
Yes.
And then I go out. So I have 2 outgoing and 2 ingoing.
3. Yes. 1.
No. One goes in. No, that
three.
goes out in your drawing.
Okay, let's repeat the drawing because. No, I
Because
put-
no, I'm looking at the picture upstairs. Sorry for
here.
being such a nuisance, right? But if I look at that vertex, I see 2 outgoing and 2 ingoing. So how do I count the valency of that vertex?
So in this case, you should just imagine that this is half an edge, and this is half an edge, and this is half an edge. So it's 3. If you want, you don't have outgoing, because the other half edges in this type of drawing would be these ones. But this is depending on how you imagine it, but it's equivalent. So in this drawing, the half edges, I'm imagining them like this. And then it's easy to count the valency, it's just 3. In this drawing, you have like the double of things, but it's because I'm drawing half an edge like this, and they form an edge like this. But it's two representations of the same object. You're welcome. Okay. So, yes. Now that we hopefully all understand what these maps are and which notations I'm using, let's explain how to encode these guys with permutations. Then you should even see that picture clear. And this will also be a little connection, I guess, to Danilo's course. So maps with labeled half edges and n boundaries are in one-to-one correspondence to triples of permutations, satisfying some conditions. So we call them sigma, alpha, phi. They are permutations acting on a set H. This set is the set of half edges and then we impose that the cycle type of alpha, the cycles of alpha are all of length 2. You will see why when I explain the correspondence if you're not already seeing it. And then we also want that these 3 permutations, when you multiply them, they give you the identity permutation. And that you have n special half edges. So you have a tuple of half edges, R, given by R, in such a way that no 2 elements of R are in the same cycle of phi. Okay, this may look complicated, but it's very easy. You will see it when I explain the correspondence. So, to describe this correspondence, we start with a map, and we want to build 3 permutations. Yes?
Is that h to the n? I don't understand what that
Yes, h
symbol means.
to the n.
And
So
what does that mean?
this is a tuple with n elements. An n tuple.
Okay, thank you, yeah.
So sigma will turn around vertices counterclockwise. This is a convention. You can take another convention, but you need your conventions to be compatible. So I'm just taking one that should work. Then alpha pairs half edges into edges. That's why alpha has to have cycles only of length 2, because we want it to be something that just pairs things. And then phi goes around faces also counterclockwise. So for example, if we have an hexagon, phi will be going from this half edge to this half edge to this one, like this. Okay, and then why do we have this condition over here? Yes?
So H is the set of half edges.
Exactly.
Sigma, alpha, and phi, what are they?
They are permutations acting on 8.
Ah, okay. Thank you.
So R is an element of H to the n. So R is an element of
R
eight.
is an element of 8 to the n.
Okay.
It's an n tuple.
Okay.
Yes.
Thank you.
Sorry, the handwriting there was a bit too smashed. Okay, so a little drawing to show why we have this type of identity. Now I'm using the ribbon graph representation. You can check that with the other one, you will get the same. So we start with this half edge. And then we have to apply phi that goes around the face, counterclockwise. So phi will send this half edge to this half edge. Then you apply alpha that pairs half edges to form edges. So it just goes from this one to this one. And then sigma that goes counterclockwise around the vertex. So this one is the one, let's say, belonging to the vertex, incident to the vertex, and sigma, it will just send it to the previous one, incident to the vertex. So it comes back to the original one. So this drawing justifies why we have this.
Sorry, can you show this phi times alpha times sigma in the triangle there?
Here?
Yeah.
Yes. I mean, that drawing is a local drawing around any vertex if you want, but which one do you like? This one?
Yeah.
So we start, for example, from this half edge, the one that belongs to this triangle. Then phi will send it to this one, afterwards to this one. So it just goes around the face counterclockwise. So first it goes to this one. So yeah, okay, sorry, this is on half edges, so it should be, well, it's a bit misleading in this drawing. It should be this one and this one. Hopefully it's not too confusing. Otherwise I can do it here maybe, but it should be the same. So this one goes to this one by phi, then alpha just pairs it to the other half edge, and then sigma just takes it to the previous, well, to the next edge in the vertex. So this is phi, this is alpha, and this is sigma. You can see that it's actually exactly the same I did here, just here you didn't have the rest of the drawing. And here you can see it as well. The problem is that maybe it's less clear. Like you start with this one, you send it to this one, you pair it to this one, and then you go back to this one. It's the same.
Excuse me. I'm slightly unsure about what you mean by a half edge. By half edge, do you mean one of the lines that go all the way, or by half edge, do you mean half a strip that emerges from a vertex? Because that's what I knew by what half edge meant. Like from a node, half a strip comes out which will be glued with half a strip that comes out from some other node.
Yes.
But it seems to me that here, when you say half edge, you mean the edge, the line that forms, that's at the edge of a strip. So I want to know, is that what you mean by a half edge
Yes,
here?
so this is an important question because I'm mixing two different representations.
Okay.
So in the different representations, these half edges are like different things. Just that it will just encode the same problem. So in this representation, this is the ribbon graph representation.
Yes.
I'm doubling, I'm making the edges fat.
Yeah.
So when I want to say what an edge is in here, it's just this whole thing is the edge. So in this drawing, the two half edges are the two boundaries of this band, if you want.
I see.
In this representation, it's what you mean. Since I'm making here the edges like simple thing, like a normal graph, if you want, then half edges are like just the half of the thing. I'm just using both because in some settings it's more typical to draw it like this, in some settings it's more typical to draw it like this, and sometimes this one is more clear, sometimes this one is more clear. So I want you to understand everything because I want to show you that this is equivalent to another model, for example.
Right. So when you say half edge there, you mean the edge of a strip.
Exactly.
The whole edge of the strip. Okay,
Yes.
thank you. Yeah.
But it's equivalent to what you were saying.
Okay.
Yes. Okay.
So I think just to see if I understand. So locally, your graph will be, you take some amount of half edges, and your first step is to clump them into spiders, right? You take one vertex and you put a lot of things, a lot of half edges out, right? And then your sigma tells you the cyclic ordering at each spider, right?
The sigma, yes.
Yes.
Exactly.
Then the alpha tells you how to pair spiders. So it's like I have this, and the alpha says, okay, connect this with that. And then finally, the phi is what gives you the disks. What
Yes.
ensures that whenever you pair the spiders, you're actually creating disks, right?
Exactly.
More or less, I think.
Yes, exactly.
Right.
So,
Okay.
yeah. I usually think of it the other way, but it's exactly equivalent. So what I think, to go this way, I described more this way, but to go this way, you start with 3 permutations and the set of half edges, and you just build polygons with your phi. Your phi will just build polygons for you because it builds the faces. Then the alpha pairs the polygons, and then the sigma has to be compatible. But it's exactly what you said, just reversed. And of course, these two things are equivalent because of graph duality. Okay. So, where was I writing? Here. Finally, we can say that the Euler characteristic of these combinatorial maps, now I'm calling combinatorial maps this permutation data. So it's just the number of cycles of sigma, which is the same as the number of vertices. Minus, yeah, so they are permutations. So they have a representation in these joint cycles. This is what I mean. And you know that the cycle type is well defined in the sense that the lengths of the cycles are, I mean, you can change the representation, but it's the same.
And the phi of the root is the same phi. Here that you wrote the phi of the root is identity, and the other one right here. So this is the same phi as
No, sorry. This is from another life. Yes, this is the isomorphisms of graphs. It's different. Okay. So it's the number of cycles of sigma, which is the same as vertices, minus the number of cycles of alpha, which is the same as edges, plus the number of cycles of phi, minus n. So this is the same as the number of total, so the total number of faces, and this is the number of boundaries. And since they are boundaries, I want them to contribute to the Euler characteristic, so that's why I'm like subtracting them. Okay? So yeah, I can maybe write it. Number of cycles of phi containing a root. Okay, and then I could do an example, but maybe that would be a bit too boring. Maybe I will leave some examples for the exercises. Yes? Or you really want an example?
No, Elba. This is very nice. So essentially, you so in the standard formula of Euler characteristic, I will, you know, if I have a certain Riemann surface with certain genus and boundary components, then we remove the number of boundary components, right?
Exactly.
So essentially, that's why you are removing n, I suppose. Yeah.
Yes, exactly.
So you are trying to recreate kind of, you know, number of faces, number of edges. Kind
Exactly.
Of formula.
Yes.
Thank you. That's nice.
Yes, yes. And yes, and I'm not writing this is equal to 2 minus 2g minus n, because this is also okay for disconnected maps.
Yes.
Okay, so, and we will actually use it for disconnected.
So isn't chi also a function of phi?
Sorry?
Isn't chi also a function of phi? You have I'm not sure if it's a typo or there's something I'm not getting.
Sorry, I cannot hear.
Chi as a function of sigma and alpha, but isn't it also a function of phi? You don't have it.
I?
Phi.
Phi.
Yeah, like go down.
Yes?
It's a function of phi, no? You have it.
Yes.
But it's determined.
Yes. Okay, sorry. This is just determined by this.
Okay, yeah, by that condition. Very good.
Yes,
okay,
that's why
thank you.
the phi is redundant. So I could have said that this is just two permutations, and then I can remove this condition. But I think it's a bit clearer to say it's a triple and it satisfies this, then the picture, the geometric picture is very clear. But then, of course, the data is just the two guys. But yeah, very good. Thanks for the question. Okay. So I will leave maybe some examples for the exercises if someone wants to check that this actually works in some example. And I will continue. So in the beginning of the lecture, I was talking about maps. And now I'm talking about these maps with labeled half edges. So we need to relate these things because we actually care about maps, not about all these labeled things. Because we are like overkilling a bit. So let's see how we deal with this. Can we go to our unlabeled maps? So first of all, observe that there is a canonical way of labeling boundaries. Sorry, what am I saying? So imagine that you have here your polygon that is your first boundary, and it's rooted here. So there's a canonical way of labeling because you just start from this one and you go around it counterclockwise. Then this is boundary 1. And then you take another one and you can choose. Either you continue or you can even say like, okay, I start again, but then I remember that it's boundary 2. I mean, I'm just pointing out that there is a canonical way of labeling the boundaries, but no, the same doesn't happen for internal faces. So we need to kind of get rid of all these labelings that we introduced in internal faces and that they were not there before, and that they don't contain information about the geometry of the objects. So now, unlabeled maps. So I'm putting it in parentheses because this is what I call maps in the whole lecture. But I want to emphasize that it's unlabeled, are in one-to-one correspondence with a sigma and an alpha acting on the half edges. Now again, I'm omitting the phi because you already know that it's redundant, such that exactly the same as before, so I'm not going to copy it again. And now you need to quotient out by something. So you just want to identify the sigmas and alphas. Will this be a mess? With guys like this. Tell me if something is not readable. So what is this gamma? Gamma is just a permutation acting on the half edges in such a way that it fixes the boundary. It's the identity in the boundary. So yeah, this is the subset of half edges belonging to the boundary. And yes, this is the identity at the boundary. And this gamma, so this is what it is precisely, but morally, just to understand, it's just a relabeling of the internal half edges. And this is this HI. So yeah, sorry, this is.
So is this like a mapping class group
you could see it like that, like some kind of discrete mapping clause group action. I guess, yes, makes sense. So yeah, just because I put many things together there, I'm considering now a decomposition of the half edges into boundary half edges and internal half edges. This is internal. Okay, and now we have what we wanted. We have a one-to-one correspondence with just some permutations, and we can just use group theory, representation theory on this side, and these topological objects. So we can use the power of both and go from one side to the other. And actually, with this one-to-one correspondence, you can very easily make precise what we mean by automorphism of a map. So if we have a combinatorial map with sigma and alpha acting on the half edges, we call gamma an automorphism if gamma is acting on the half edges, it's fixing the boundary, and these guys are actually equalities. So we actually have that they commute with sigma and alpha. So okay, if you think a little bit about it, you can realize that these type of gammas are giving you the symmetry of the graph. So if you have a symmetry of the graph, this will be encoded by this type of alphas, the ones that commute with alpha and with sigma. So that's why we say that those are the automorphisms. This is the first observation. But okay, maybe you can also try in some examples if you don't see it. And the second observation is that actually if you have boundaries, so some phases in which we marked some edges, so n is bigger or equal than 1, so n is the number of boundaries, then the automorphisms are trivial. So okay, I'm telling you what automorphisms are because I want to be precise in this course, but actually they will not be needed so much because in topological recursion, the best thing is to consider boundaries. So almost all the time we will not have automorphisms. But yeah, if we want to do the case n equal to 0, in which we only have internal faces, then your graph can have symmetries. So yeah, just a simple example, but maybe you can, maybe you will also do some in the exercise sheets if you want to practice with this definition. This guy, for example, has automorphisms because it has this symmetry. So you can exchange half edges in such a way in which you will leave everything the same. All the incident relations at every vertex. You have this other symmetry. So this is what we mean here. Okay, and I forgot something very important. Of course, here what I mean is if the graph is connected. Otherwise, this observation is not true. Because you may have a boundary in one connected component, and in another connected component, you can have automorphisms. So yeah, here I mean connected. Okay. And we are almost ready with the permutation model. Now I just want to point out how many guys are there in an isomorphism class. So yes, the number of gluings, if you want, of a combinatorial map is the number of elements in the class defined here. So the class belongs here, so it's in one-to-one correspondence to maps. This is just given by the number of relabelings over the number of automorphisms. And this is just group theory, actually. It's just the orbit stabilizer theorem or something like that is called. But okay, it's very intuitive. Know what's going on? So yeah, just I didn't write down what is this. This is just the relabeling of the internal half edges. And for example, if we consider labels in the internal half edges that are completely arbitrary, then this would just be the cardinality of the half edges factorial. But if it's not arbitrary, if you put some rules, then it may be smaller than this. So, okay. Okay. So now we finished with this, and we will need this tool to make the relation with matrix models. Are there some questions about this? No? Okay. So now we will do a little detour to define our special type of maps that we will call simple and fully simple maps. So for the moment, there will not be much motivation apart from the fact that this is something nice to consider combinatorially. Oh, by the way, I completely skipped the motivation part of why you care about maps in general, but okay. I guess it's clear for many people here, but maybe let me just say it quickly. So, okay, there is the combinatorial motivations. These are important objects in combinatorics. And they have been studied since a very long time. In the 60s, started studying them a lot. And then generating series came into the picture, and many things happened since then. But still, it's an active field of research nowadays in combinatorics. Then these guys also help you study the large geometry in like quantum gravity, statistical physics model, and this type of thing. So you just consider discretization of surfaces, and you send the size of the map. So, for example, the number of vertices to infinity, and then you study universal properties, you study analysis, critical exponents, these kind of things. And they are also important because they are Feynman graphs of matrix models, for example, in Chern-Simons theory. But we will see one of the simplest examples, which is the one Hermitian matrix model in this lecture. So for me, these are the clear three motivations. Then there are others, like even they have relations to Galois theory and other things. But yes?
Sorry, could you repeat the definition of G of sigma alpha? So it's the number of elements where?
Yes, this can just be the definition. This is the number of elements in the isomorphism class here. So how many guys are we identifying?
Okay, so you take the quotient of, so it's, so it's maps of type sigma alpha but unlabeled.
Exactly. So how many they are mapped to the same unlabeled guy, if you want.
Okay.
So we had before another correspondence in which there were here more objects because they were labeled guys, and they were these guys without this relation.
Yeah.
So now I'm saying like, okay, if we put here unlabeled, how many of these will be mapped to the same guy by this correspondence?
So before your half edges had numbers and now they don't. So before each half edge had a number and now there's no numbers, you just have arrows.
Yes.
Okay.
Yes, yes. Actually, that's why I call it GL. It's like gluings. If you want, it's like you're actually counting the gluings that you have.
Okay.
You can count it with these two guys. The total number of labelings over the automorphism. Okay, so we talked a bit about motivations, and now we go to these two types of special maps. So by simple, I just mean that there will be no more than one, so this is a bit cumbersome to state, but it's very easy. No more than one boundary edge per vertex. Of course, we will also see examples, and this will be clearer. And by fully simple, we mean that it's simple and that the boundaries are disjoint. Okay, so let's do an example. I'm just drawing three different maps embedded on here on the plane, on the whiteboard. So they are all of topology, so they are all planar. But I actually want them to have two boundaries, all of them, so they are all cylinders. They are of topology 0, 2. So these are the boundaries, the ones that I'm painting now. And we want to see which ones are simple, which ones are fully simple. Okay, so this one over here, the first one is nothing. It's not simple already because in this vertex in here, we have more than one half edge belonging to the boundary that enters the vertex. And actually, it's locally exactly the same picture that we were discussing with Marta there.
Sorry, say that again.
Yes. So this vertex is simple because there is only one half edge incident to it. If we are consider that this one is the incident one, just this one. But this one, as we counted before, has 3 incident half edges. Sorry, 2. Yes, 2.
Why the previous one is not 2? Because one half edge from this one half edge from the other.
Yes, but remember that we are counting half edges. Otherwise, I would have said at most 2 edges. But I'm counting half edges, so only this half edge belongs to this vertex. If you want, we should go back to the, well, it's actually as unclear, I guess. So this one belongs to this one, and here this half edge is outgoing, so it doesn't belong to the vertex. Okay.
But when they don't have an arrow, how do you know which of them are?
It's just, you just take a convention. I'm saying like this because it's kind of natural to say like, okay, they go around like this. So this one with 5 will go to this one, then to this one, then to this one, then to this one. and then to this one. Yes. Sorry, okay, now this picture maybe it's not super clear. Yeah, so if you do it like this, maybe it's a bit more clear. This one belongs to the boundary, and it's incident to the vertex. Wait, sorry, now I'm confused. Am I saying this wrong? Yes, of course, yes. Okay, forget. So this one belongs to the boundary and to the vertex. This one is outgoing, so it doesn't belong to the vertex. This one belongs to this other vertex. So that's why there is only one. But in here, there are three. There are two, sorry. This one and this one. Okay? Yeah, if it's easier to think it with edges, it's like exactly the same thing. With edges, it's just here you just have two, so it looks like a simple corner of a polygon. And here you have identified edges, so this is not simple. Maybe it's simpler to think it that way. Then this polygon is simple, but okay, since the map already has this vertex which is not simple, then this is not simple. Then this one, all the vertices are simple. They all have exactly two edges belonging to a boundary incident to it, belonging to a particular boundary incident to it. But in this vertex, these two boundaries touch each other. So it's simple, but not fully simple. This is what I mean. And not fully simple. And this one is simple and fully simple, because they don't touch. Okay. And it turns out that a little spoiler or motivation for later, it turns out that these fully simple maps are kind of the dual objects in some sense with respect to topological recursion, but also with respect to many other things, with respect to some free probability motivations and some other things that we are still exploring. So they are kind of the dual objects to ordinary maps, the ones that I defined in the beginning, in which we allow all these things to happen. And maybe we will also see this from the perspective of the matrix model. We will see if we have some time. So observation, we can make a characterization of what these conditions mean in the permutation model. So if we take B to be the union of phi orbits, of the elements of R, so remember that R was the tuple of marked edges. So phi orbits of these elements just means the set of boundary edges. So this is just the set of boundary half edges, if you want to be precise. Half edges. So B is just the set of boundary half edges. Then a map is fully simple if and only if the elements of B lie in different sigma orbits. This is just a translation into group theory, okay? Not too much group theory, but of this condition that I was explaining here. This will be useful to make the connection with the matrix model. Okay, so now I guess we are ready to talk about generating series of these objects. So every time that you're interested in studying families of objects, it's a good idea to put them to organize them in generating series for various reasons. Well, first of all, because you can do algebraic manipulations. So, I don't know, inductive construction of these objects translate into relations of the generating series. And also the generating series are cool because they allow us to do analysis, for example, for these critical behaviors that I was talking about. These are motivations to consider generating series. But in this lecture, I guess we will not do much analysis, we will do mostly combinatorics. So this will be formal power series in most of the talk. Maybe we will talk about some of the analytic properties, but not much. So we consider IF of M to be the set of internal faces of M. Well, I'm getting a bit too vague with the notations, internal faces. Then I'm considering a set of graphs in which we fix the topology, Gn. We fix the length boundaries by L1, Ln, and we fix the number of vertices. So, just what I just said, this is maps of topology Gn with boundary lengths L1, Ln, and V vertices.
Internal means the label ones, right? The ones you shaded.
Exactly.
Okay.
Well, it means the ones that don't have roots, so the ones that are not colored here, for example. Opposite, yes. Yeah, so boundaries are the marked ones, internal are the other ones, the ones that we needed to relabel and everything. So yeah, there is actually one condition on the degrees of the internal faces. This is a bit technical condition that we actually could remove, but I will put it and then try to write down all the formulas correctly, so it will be a bit easier for me. But you can actually remove this condition. So internal faces of degrees between 3 and D. Okay. So this just means that we don't want to consider one-gons as internal faces, or bigons, but we allow triangles, quadrangles, pentagons, blah, 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 until digons. And D is just some boundaries to make our life simpler, but with some limit arguments, you can actually do it for unbounded D as well. Okay, so yeah, I didn't write down the genetic series yet. Are there questions? No?
No D in the definition of your M?
Yes, it finishes here.
No, I mean you have G, N, L, V, and there's no D dependence.
V is the number of vertices. You mean that I didn't put D here? Yes, yes.
Yeah.
Okay. We could maybe add D as well.
Okay, but you fix D maybe for each generating.
Yes, yes. We fix D. Some integer bigger or equal than 3. Okay, so the generating series. Maybe I don't have enough space here. Well, I will try. Fine. So generating series of ordinary maps of fixed topology, fixed lengths, then with these parameters for the internal faces that we will omit most of the time. And there is also a parameter u for the vertices. This will just be the sum over possible numbers of vertices that go from 1 to infinity. We put a weight for the number of vertices to keep track of the number of vertices. And then we sum over maps that belong to our set. We divide by the number of automorphisms, and we put weights t, k, where k is the length of every internal face. So here we take the product over internal faces of M.
I haven't understood what are T3 to TD.
Yes, they are just parameters that will count how many triangles you have, how many quadrangles, and like this. So they are parameters to count the number of internal faces of a certain length. Okay, and this is the ordinary generating series. And we have the analog, which is the fully simple one, that I will write much more quickly, because you can guess how to fill in the details. It's just the generating series for fully simple. It's exactly the same. It's just that here you need to sum, of course, over fully simple maps. And then we are missing the correlators. I write them here. The correlators will just be summing over all possible lengths. So I'm just putting the generating series with fixed lengths on top. By the way, here and here I'm already omitting all these parameters, but they are there. They depend on those. And then in the denominator we just put x1 to the L1 plus 1, xn to the Ln plus 1. So the x's now keep track of the lengths of the boundary faces. So now we are summing over all possible lengths for boundary faces, taking our generating series with these fixed lengths and adding some variables that keep track of these lengths. This is what we are doing. And then there is the analog guy for fully simple that we call x. We take some variables w. And this one I need to write down a little bit because it's fully simple, as you can imagine. But now we change the type of generating series and we put our variables that keep track of the length in the numerator. And we also do L1 minus 1, Ln minus n. So this may sound a bit mysterious, like why are you putting this in the denominator and with a plus 1 and here in the numerator? This is just because I will relate these two problems and the formulas will look nicer.
Sorry, I didn't understand the upper part.
Yes?
Yes. What is this last one? Fs?
Yes.
What does it mean?
Fs is the generating series of fully simple maps that looks exactly like this one, but instead of summing over all maps, you just sum over fully simple maps. So I'm not copying the same thing with fully simple here because it takes some time, but
And in the upper one, what is the product of what? The very last
this
below.
this is the product of tk, and the k's are the lengths of the internal faces. So these are just parameters that count how many internal faces of every degree you have. Sorry. This is f over running over internal faces of M. And then you take the product of t length f, which is what I'm describing. So here you will have, I don't know, generating series with t3 to the 2. This just means that you have two internal triangles. So you encode this information in your generating series. You will be able to extract coefficients as you want, so you can recover this information.
Could I ask? I don't see why it's obvious that the lengths of the faces won't exceed d. So in the top formula you have variables t3 up to td, right?
Yes.
And then you say that you're taking t subscript length of the faces.
Yes.
I don't see why the degrees of the vertices being constrains the length of your faces. Like I can take a polygon with arbitrary length and vertices of degree.
Sorry. This is a confusion in this definition. The constraint that I put is that internal faces have degrees. That just means the length. Sorry.
The length of the
Degree
faces.
is the length of the face.
Okay.
Sorry, I'm using different words.
I
fair enough. So degree of a face is the same as length of a face. So it's
right now, I copied degrees of vertices because I mixed that up. Okay.
Okay.
I see. and another question I had is, so w and x, will they be related by some exponential logarithm? Because is that why you're changing the variables like that?
No, I wish it was that simple, but it's not.
I see.
But the relation for 0, 1 will be very, very simple. And that's how we modeled what to put in here. Well, we actually took the typical convention in physics, at least the one that I know the most, which is this one for ordinary. And then for this one, we just adapted what to put, so the formula for 0, 1 looks nice.
Thank you.
Yeah. You're welcome. OK. So now we are ready to start the connection to the Hermitian matrix model. And this is... I guess I should warn you that it's substantially messier if I want to do the details, but I will try. So I don't see the other organizers, but I guess I can say I have a bit more than half an hour. But not much more, because then we have to eat. So I will try to finish this connection, because otherwise we will be doing very bad with time. I'm calling these correlators. It doesn't mean much, but correlators from physics. This will be the correlators. Well, actually, usually you call correlators the WN. So I guess I'm calling correlators because of professional deformation from topological recursion, in which you always care about GN. But usually you can call correlators of the one Hermitian matrix model WN, and then you have a topological expansion, and then you see the WGNs appearing. Now I'm calling correlators the WGNs.
And in the capital X, those are W or the...
They are W's, yes. So these X's are small x's, and these W's are small w's. But they are, I mean, it's not a coincidence that this is called the W and this is called X. Because these will be like dual objects. That's why I'm putting the same names for the variables. So, okay. Connection to the one Hermitian matrix model. So now we consider the space of n times n Hermitian matrices. And we take matrices on it. And on this space, we introduce the following Lebesgue measure. So sorry, now it may look like I'm going crazy changing topic, but my goal is to relate these two maps, okay? So it's not so far from what I have been doing until now. Imaginary of A, I, J. Is this readable? Okay.
Sorry, could I ask a
Yes.
question about the... So you said down in the definition W, it's possible to have a boundary of length 0?
Yes, that's a weird thing, but for disks, for 0, 1, we consider the very weird map of just an isolated vertex, and this is a boundary of length 0.
So that's the only,
You could remove
the only
it
one?
because,
I'm sorry, okay, I'm sorry. I guess somebody asked that before. And then finally, maybe I missed.
For higher topologies, I just put bigger or equal than 0, but
Yeah.
I could omit it because they are all, I mean, you cannot just have a boundary of length 0 and the others of positive
Yeah.
length.
And can you say again what the FS in the definition of X is?
Sorry?
Can you say again what the definition of FS in
FS, yes. This is
the... Thank you. Okay.
the
sorry.
generating series
Yes. Sorry.
for fully simple maps. Exactly as the ordinary one, but summing over fully simple maps. Is it clear? Yeah? Okay. Okay. So we put this Lebesgue measure on our space of Hermitian matrices, and we consider the Gaussian unitary ensemble. So this is abbreviated very often as GUE. Okay? And then this is described by the Gaussian unitary measure that I just write down. Then you take the Gaussian, as you can imagine, but for matrices. So we just take trace of a to the square over 2. Then we want this coefficient n over u. This is exponential to the minus all this thing. But then we want this to be a probability measure. So we divide by something that will make the integral of this thing to be 1. This is what the meaning of this guy is. So just to do this, I mean, I'm not going to do this computation. But you just need to put the result of this computation. Sorry, that is a bit smashed again. U, yes, sorry. This is a U. It's the variable for the vertices in here. So yeah, I repeat. I just put this guy, which is the integral of the whole guy here, so that when we integrate here, we just get a 1. Okay, that's the motivation for that guy. Then we can compute, this I will not do either, but it's an easy computation, that the matrix elements have covariance, something quite simple. This is the indices of the entries of the matrix. So it will just be given by u over n of delta of AD. So we want these two guys to be the same and these two guys to be the same. So we want AD, delta AD, that will be 0 when they are different and 1 when they are the same, and delta BC. Okay? Sorry? U is just a parameter, but it will be eventually the parameter for the vertices, for the number of vertices. V is the number of vertices, and U is the variable or the parameter that keeps track of the number of vertices, because it's U to the V. So if you want to know how many maps are there with 2 vertices, you will extract the coefficient U to the 2. And thanks to that U, you can do that. Okay. Then I will state for you, I will also not prove this, Wick's formula, which helps us compute any, we can put here any polynomial on the entries of the matrix, and it will tell us how to compute it, just using these covariants over here. This is what Wick's formula does for you. It's a very useful thing, and also kind of cute. It kind of goes from combinatorics to this GUE. So we just take products of certain monomials. I just put an even number because from the formula it will follow quite clearly that if I put an odd number, this will be 0. So I just take, I'm not saying what I mean by this. So when I put this R angle, L angle, I just mean that this is the integral of dot, whatever is in here, against the Lebesgue measure of GUE. Okay, so this is what I mean by these brackets. And here I just sum over all possible pairings of these indices. So this is what this notation means. This is set of pairings of the set 2M. Okay, so I'm pairing all the indices in here in all possible ways. And then I take the product of R, this is too small, right? Okay, I will continue here. What you should put in there is product over all pairings. Not over all pairings. Over all the pairs inside a specific pair of the correspondent covariant. This is the set of pairings. Okay, is it clear what this theorem does? So it just takes for you products with 2M factors, and it tells you that you can compute it just from these guys that you calculated here. So you don't have to do all these crazy computations. You just compute this one once, and with that one, you just take all the possible pairs and the products, and that will give you the right answer. This is what this theorem is telling us.
What is xi here?
It's just,
Some random variable.
yes, exactly. So you're computing the expectation value of these random variables with respect to this measure. This is what you're doing. And in our case, they will just be entries of our Hermitian matrices. But this is more general than Hermitian matrices. Okay, so now I consider the measure that comes from the Gaussian measure, but that will also take care of the internal phases. So here I'm talking about maps. It's like a bit cheating a little bit because you should not be seeing maps yet, but since we know that there will be maps, I'm already telling you that that's why I'm putting these names to things, so everything will match. So here we take exponential, n over u again, trace of just the Gaussian guy, a to the square over 2. And then we take plus sum from k to from 3 to d of tk, and tk will be the same as the tk's in that formula, a to the k over k. Okay, and the whole guy inside the trace, how to mark it now, is what we call the potential. if you want the potential of the matrix model. We just call it V. And okay, now we are ready to say what we want to compute, and hopefully also ready to compute it. We will see. And we will use this Weeks formula. So to keep it visible for you, if you want to try to follow the details of the proof, because I will probably not have enough space to keep it there all the time. Okay, so now we compute. Okay, I didn't say what this is. Now I'm just calling triangle brackets the expectation value of whatever you put inside with respect to this measure. Okay, so this one, I didn't write it. Very bad. So this one is bracket GUE with respect to the GUE measure, and this one is bracket non-GUE. So it's a bit more extended. So, okay, here I write the product of traces of matrices. I guess most of you saw these things many times, but maybe not all the details. So we want to compute the correlators, I mean the expectation values without the GUE. So I just expand it. This is an almost trivial step, but let me do it for like clarity. I'm just putting again what this means and writing instead the GUE bracket. Okay, so here I have my t's because the t's are not in the GUE measure. This is my k's that are a bit strange. This is not even a k, but I wanted it to be a k. Yeah, sorry, maybe this is a very bad case, but you should not confuse my use with the case. Hopefully it's clear. And yeah, I just close everything. And here, this is the bracket GUE. So I just copied the part of the measure again that is not inside the GUE. This is what.
What is D? You computate from 3 to D.
Yes, D is still the same as before. It will be the bound of the degrees of the internal phases. We don't know about maps yet in this setting, so we just take a D. It's just an integer number bigger or equal than 3. And it's to make our life simpler. We could also go to infinity, but let's keep it as simple as possible. So now the technique that we need to apply, because we are doing formal matrix models, is just we expand around the tk equal to 0, and we just exchange the integral and the expansion. This is an important step. And then there will come a lot of tricks. So this expansion will be a bit ugly big formula, but it's just expanding the exponential. And I'm taking here the weights tk. They appear here in the expansion. So I'm already putting all these outside of the integral. And then inside of the integral, you just have the products that come from the expansion of traces of a to the km and products of the traces that were already there. So these ones are not new. Okay, so here I'm just expanding the exponential. And exchanging the integral and the expansion, which is not something obvious if you are doing analysis, but since we are doing formal matrix model, this is allowed. And okay, now we want to know what this is. So I will give you the expression for this guy. And for this, you need to be, I mean, you need to have done this computation once, or at least convince yourself that this is okay. So when you take products, when you take traces of products of a matrix, this will just have this, this shape. I'm just giving it for you, but you can convince yourself that this is true with an example. Sorry, this has a bit heavy formulas. But this the trace of a matrix to the power k. It will just sum overall possibilities for these type of factors. And in the factors, there will just be entries of the matrix that are of the shape I, J, then so A, I, J, A, J, K, and like this. So they will have this cyclic structure. Okay, probably you've done this computation, so it doesn't sound too weird. And then I still have this whiteboard. Nice.
The first multiplication was without GUE, and the second one is GUE. Yes. I don't understand why the first line is normal.
Yes, so this one is what I want to compute. And then I'm just writing the same thing and the parts that are not there in the GUE. So what I called GUE is just this part with the square. So I'm just copying the other part. So that's why now it transformed into GUE. Okay. So now, using this, we want to know how this looks like. Is there a problem? No. Okay, so I will just write what this red factor over here is. I don't want to write the factor again, so sorry. But okay. So now, okay, there will be some mysterious things appearing that will already tell us that this will probably be related to maps. But let me first write them and then justify them. So we have these correspondences from set of half edges to 1 to n. And then this product over half edges of the entries of the matrix given by these maps over here, GUE. So you can see that this structure should be coming just from this formula that I wrote here. But then why all these edges? Okay, so we are considering now a decomposition of H. And these H's will just be some structure that we give to the indices to keep track of the K's and the L's from the formula. And this K's and L's will be, of course, related to the K's and L's from the lengths of the maps. Okay? So this will just be these sets.
So now you have that Wick's lemma.
Exactly. Exactly. I need to apply Wick's lemma to these guys to compute those guys. And Wick's lemma will create for us the edges of the map, as you can already predict, maybe. But these guys will be the indices of the edges of the boundaries and the edges of the internal faces. And then I still need to tell you what phi is, and phi will of course be the one going around the faces of the map, but at this moment we still don't know about maps. So I just need to define what it means in here. And this is just fixing the face and going to the next L in the face, Okay? And now when I talk about phases, I'm just talking about this special structure that I gave to these indices that appear in the formula. But they will be related to the phases. So I just used this type of shape that the traces of a power of a matrix have to write this down like this, and used these sets to encode all the indices of the formula. This is just what I did. And now we use weak theorem. But it's small, so we should go to the next one. And I will try to finish in less than 15 minutes. So, okay, now we use Week's theorem. So Week's theorem is the sum over all possible pairs of the guys appearing in the product. So we can encode this as just some fixed point free involution. So this is what this set means, fixed point free involutions. And this is inside the symmetric group on the edge elements. Okay, so this is just pairs. So with this fancy vocabulary, I'm just saying that this just pairs things. So it's Week's theorem, it's nothing fancier than that. And then we take products over all possible pairs. So in this case, it means half edge and the corresponding half edge given by alpha. I'm already talking in terms of maps, but remember, it's not cheating. I'm just applying Weeks here. So this is just all the guys that appear in the cycle of alpha. So the alpha here will pair our H's. And then I just need to put what goes in here. And this is just by Week's theorem given by all these covariances that we already know how to compute. Now, how do they look in this case? They just look like this. And then you can check the details probably better in your paper if you have the Week's theorem in front of you. So I'm just pairing all the guys appearing in this product with the alpha. So I just need to put here the guy and its corresponding pair. J alpha phi 8. Okay, and this is, well, I need to close the triangle bracket, GUE. And these guys we know how to compute because of this formula, actually. So now we use that formula to compute those guys. Well, we know that this guy has to be equal to this guy, and this one has to be equal to this one. So, okay, we say, okay, this one, 8, has to be equal to alpha phi of 8. And this one equal to this one. But these two things are equivalent, because alpha is an involution. So I just can put it on the other side, and it's the same. And also, the number of cycles of alpha is just given by the half edges over 2. And I'm now, again, cheating a bit, calling these already half edges, but it just encodes the indices of the formula for the moment. Oh, sorry, I mean cardinality here, of course. Okay, are there some questions before I erase the Weeks formula? Otherwise, we can do questions in the end, but. Then I keep going to try to finish not so late. Okay, so now again I want to write that this is equal to the sum over the fixed point free involutions. And then the value of this guy over here that I just erased. So it gives us this u over 8 to the number of cycles of alpha. This just comes from the covariance of these, the formula for the covariance of these guys. And then the products of the delta Kroneckers. So this is just applying the formula that I just erased again. Okay, and then okay, now I want to go back to what I had before, that is hopefully still there. Sorry, this is a bit tough with these small whiteboards. Okay, so we come from here. We just gave this expression to this little guy here, and we kept going until there. But now I want to go back to this equality. So it's very good that it's still in there, otherwise this would really be very, very messy. So I go back to this equality, and I use everything we learned about the guy that I put in red. Ooh. Okay, so maybe I will just rewrite everything so it's very clear. Only it's as clear as possible. So you can see that I'm still rewriting the formula with the R, the T's. And then here we put the sum. Now we put already what we learned. We put the involutions, the fixed point free involutions. We put the guy that we computed. And then we should not forget about this map that was there. This sum over here we didn't take care of yet. And then we put the Kronecker deltas that we computed. Okay, because the 8, maybe this was not clear, sorry. When I said that this is equal to that, I didn't mean this sum. I just meant this guy over here. Okay? So for the application of the Weeks theorem, this is what was in here, not the sum. So the sum, I'm just keeping it, and I just need to put the result of what I computed. And now, let's think a little bit. So these guys will be 1 just when this H goes to G8 is constant. So okay, I'm saying that these guys will be 1 when this happens. When this is constant along the cycles of this permutation in here, okay? Because H has to be equal to this, for this to not be 0, for all the H's. Okay? And then we can just compute this. This is kind of just the n colorings of all the cycles of this permutation. So maybe let me just change the pen, because this one is finishing. I'm making a mess with all the pens. Okay. So now I can tell you with this justification over here that this is just, I mean, the n colorings of the cycles of this permutation is just n to the number of cycles of this permutation. Oh, this is so much better. Okay. Now we give a name to this other guy. You probably can guess what it will be because we are just using the same language as for maps because we want to get there. So this will just be sigma to the -1, but the number of cycles of sigma to the -1 is equal to the number of cycles of sigma. And we already completed almost the connection to our maps. So, are there some quick questions before I erase this?
The first H is a typo, right? That's that.
Sorry?
It says U over H is U over N.
Ah, yes. Where is 8? Ah, yes, yes, yes. Thank you. U over N. Yeah, sorry that this proof is a bit technical, but then you will be able to see how to get the topological recursion from both sides, so it's kind of nice. So, okay, we just finish with 1 over z, and now we sum over sigma alpha, which just be combinatorial maps with n boundaries of lengths given by the L1, Ln. 1 over the relabelings of sigma alpha, which are just counted by this product. This tells you how you can move around all the internal faces of degree r. And this tells you that every face of degree, This tells you how you can move around all the internal faces of a fixed type. There are r of them, and this tells you that every internal face of degree m has a cyclic order. Okay, so this permutes the internal faces, and this tells you that they have a cyclic order. This is, you can see here. Since we gave this structure to the labelings of the internal faces, those are the number of relabelings. Okay? And then we just compute, we just put what we computed, the n to the correct power in here. And we'll just write it here. This is n over u to the number of cycles of sigma. This was computed here. Minus the number of cycles of alpha. This guy appeared here. And plus the number of cycles of phi minus n. And this guy is equal to r. R is the number of internal faces, and this is the number of faces minus the number of boundaries. So it's the number of internal faces. And and then there is a little mismatch with the u because there is a guy that doesn't have a u. Where is it? Ah, here. This guy doesn't have a u in the denominator, so I need to add it. And then we just add the products of the t's sub length of the internal faces, and the internal faces in terms of the permutations are just the cycles of phi restricted to the interior faces. So they are just the cycles of the interior faces. So I'm just taking products of our interior faces and getting the t's as we had in our formula for maps. And now we just have a sum over combinatorial maps, but these guys have labels everywhere that come from the matrices, the labels of the matrices, of the indices of the matrices, sorry. So we want to transform it into unlabeled, but we know how to do this. So okay, this delta connected is because I just removed this 1 over z. I will say a couple of words about it in the end. So I'm just taking now isomorphism classes, so unlabeled maps, so just maps, with delta lengths, again, given by the LIs. And then in here, we just put n to the Euler characteristic of the map, divided by the number of automorphisms. I will tell you why. And again, the product of the t's. And the same in here. So what are we doing here? We are just, in this equality, we are just multiplying by the number of guys in every class. So multiplying by this guy. This requires quite some techniques. Yes, just multiplying by the number of guys in the class that I told you before, that is the relabelings over the automorphisms. Okay, so we need to multiply by this guy to be able to sum over maps and not labeled maps. So this just kills our realm and makes this guy appear. Okay, and now we are over. We made the connection that we wanted. Maybe the only thing that I need to justify is the delta connected. What is this? Yes. This one?
No.
This one?
Yeah.
Oh, sorry. Yeah, I will rewrite it. So now I'm summing over delta connected. Then I will tell you what it means. Delta connected maps, so unlabeled maps, which are these isomorphism classes with delta lengths, so lengths of the boundaries fixed, given by the LIs, as before. So that doesn't change from here. And delta connected just means disconnected, such that each connected component has at least one boundary. Okay, and why is this? This is just because we were taking all the time 1 over z, and I didn't emphasize this too much, but z is just the generating series of maps without boundaries. So I'm just removing here the connected components that don't have boundaries, and that's why I get delta connected in the end. So I just finish, and the next day I will start with some pictures that make a summary of this proof. So you can ask questions if you didn't understand some details, and we will prove the topological recursion for maps. Thank you.